Welcome back, everyone. So in this video, we are going to be talking about force. What is a force? What are the different kinds of forces that are responsible for the universe looking and behaving the way it does? And then we'll kind of wrap up this video by talking about Newton's 3 laws of motion. What do they mean? How do they work? All that kinds of good stuff. All right, so let's start with the definition of force. Yeah, I think that's a good place to start when discussing forces for the first time. Right? A force is a push or a pull. Right? A push or a pull. Now, it's important to recognize that this push or pull, this force, does not have to be due to direct contact. Okay? I can push my board, I can pull my board. That's a physical contact. That is a force, of course. But we can have forces act over distances. Think about gravity for a second, right? We have a force that we call gravity that keeps our planet revolving in an orbit around the sun. There is no physical contact between the sun and Earth, so obviously that force has to be applied over some distance, right? That's called a field force. Force that kind of exerts a field sort of in all directions, right? We have an electric field, we have a magnetic field, same concept, right? Cool. So now let's talk about what are known as the fundamental forces. Okay? So these are forces that basically govern the universe, right? If these forces were any different, the way we see things, the way the planet's formed, all sorts of different things can go awry if these forces aren't exactly the way that they are. Okay? Now, I'm going to make a list. 1, 2, 3, 4. And I'm going to write down each force. Now, I'm going to say each force and do 1, 2, 3, 4 in increasing strength. Right? So the first one I'll put down is the weakest. The last one I put down is the strongest. Okay? So the first one we're going to talk about is gravity. Yeah, that's right. Gravity is the weakest fundamental force. I'm not really sure why. There are some hypotheses floating around there out in the world of physics and cosmologists and stuff, but gravity is the weakest force. It is also a fundamental force. Okay? Gravity is responsible for forming planets, stars, galaxies, all sorts of that kind of stuff. Right? It keeps us on the ground. It keeps the sun around the center of our galaxy. It keeps us around the center of our sun. Right? It's very important in regards to the universe. Right? If gravity were a little bit stronger, maybe we don't exist in this particular part of our orbit, so maybe we get too close or too far away, so liquid water can't form and stay, and at which point life can't evolve on the planet, right? It's very important the way that it is for allowing Earth to have life. Okay? The next one would be the weak nuclear. All right? So the next force would be the weak nuclear force. This force is responsible for radioactive decay, beta decay, alpha decay, right? Things like that. Okay? It's not one that we really come across on our daily lives too frequently, but it is something that's out there. The third one is a bit more familiar. That is electromagnetism. Squeezed it in there. Electromagnetism. Okay, this one is very important. Very important. It's responsible for light, being able to see. It's responsible for basically all the other forces that we deal with on a daily basis. Right? I can explain to you why we are able to stand on the ground because of the electromagnetic force. Right? We can talk about pushing things in terms of the electromagnetic force. Right? That's another conversation for another day, but the electromagnetic force is responsible for a lot of the forces that we use every day. Right? And the last one, the strongest one there is aptly named because it is called the strong nuclear force. The strong nuclear force. Right? This force is responsible for keeping nuclei together. Right? Think about this for a second. You have a proton, which is positively charged, in a nucleus with one or more other protons, also positively charged. Well, we know from the electromagnetic force that those positive charges want to repel each other. So how are we able to jam them into such a tiny spot? Well, that's due to the strong nuclear force. Right? It's so strong it can overcome that electromagnetic repulsion between protons and allow elements outside of hydrogen to form. Right? It's very, very useful. Right? If the strong nuclear force couldn't do what it could do, then the sun couldn't do what it can do, which means it can't produce light, which means it can't really form. Right? And then we just got a big ball of hydrogen that's not really doing anything, and it all just sorts of fades away. Right? So those are very, very fundamental forces that are responsible for how we perceive and use the universe. Okay? Now, more locally, however, we kind of go about our business using Newton's laws of motion. Okay? Newton's laws of motion. The first one, right, there's three, and they have this is Newton's first law, second law, third law. So the order kind of matters. There's no order of importance, but that's just kind of how he listed them. Anyway, the first one is that for an object that's at rest or in motion will stay that way until an outside force acts on it. Okay, so an object at rest will stay at rest, an object at motion will stay in motion until acted upon by an outside force, which is, you can almost argue that's common sense, right? If I leave my marker right here on top of my head, it's going to stay there until I apply an outside force on it and move it. Okay? The object of motion will stay in motion. Sometimes it's a little less obvious, simply because, well, I know if I roll a ball through the grass, eventually that ball is going to come to a rest. Well, we know that that's friction. That friction counts as an outside force. Without friction, it will just keep on going, right? In space, if you throw something, it's going to keep on going until something else knocks it away. Okay? The second law. The acceleration on an object is proportional to the net force acting on the object to its mass. Or in other words, F net equals ma. Okay? Net force equals mass times acceleration. Net force, that's an important one, right? It's important to understand that the net force is all of the forces all at once acting on an object, and how do they make that object move, right? When we get into talking about specific problems, we'll break that net force down into different dimensions, and we can look at it kind of a bit more piece by piece. But the way this marker moves is due to the net force I apply to it. Okay, whether it go like this, whatever. Okay, the net force acting on that object is responsible for how it moves, right? Whether it's still at equilibrium or accelerating. Okay, and the third of Newton's laws says that for every force, there is an equal in magnitude and opposite in direction reaction force. Okay, so the way you read this is the force of the first object on the second object is equal to the negative force of the second object on the first. Okay, so what does that mean? Well, it means that anytime you apply force to an object, that object is applying the same amount of force, but in the opposite direction. It doesn't matter about the size of those objects. It doesn't matter if one of those objects becomes annihilated because of that contact. Thinking of, a bug on a windshield. It doesn't matter. The amount of force between those two objects is the same. The only difference is their direction. Okay, so if you squish a bug on your windshield, the amount of force that that bug put on your car is exactly the same as the amount of force that car put on the bug. The reason the bug gets annihilated and the car is relatively unscathed, apart from maybe a smudging, is because of the fact that the car has a much greater mass than the bug, which means it's got a much smaller acceleration than the bug. Okay? Those are the basics of force, right? In another video, we'll talk about different scenarios and how to apply those different scenarios. We'll talk about different rules when using those scenarios, things like that. But one final thing I want to leave you with is this, right? We have F equals ma, net force equals ma. Okay? The units for mass are kilograms. Units for acceleration are meters per second squared. And this has a special name, that is the Newton. All right, so the unit for force in our MKS metric system is the Newton. All right, so that's all I got for this video. Keep an eye out for the other videos about forces that we're going to kind of get into. And until next time, I'll see you later.